When we measure distances in the real world, we don't really use the Pythagorean theorem. We use a ruler. We just align it with the points like this and read the value up here. No fancy math. Or is there some hidden math behind this? We'll see. In this video, we'll teach the computer to calculate the distances in the same way we do, and see if it's better or not than the Pythagorean theorem. We'll code this from scratch, so start your favorite editor, and I really hope you go the distance with this one. Get it? Go the distance? Because we're... No.
Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now.
We'll begin in an empty folder, and I will create our one and only file for today, index.html. Now here we start to write basic HTML, and inside of the head, let's define the title for our page without Pythagoras. And I will also write this title in the body section in an h1 tag, like so. Now our page will contain two canvas elements, a left one and a right one. I will define here left canvas with a width of 300 and a height of 400. And I will copy this for the right canvas. So let's put here right, and this size will be different. This will be 500 and 500 square canvas. And I'll let you comment below why I chose these values. Maybe you figure it out by the end of the video. Now, if we save this file and open this HTML file in a web browser, it should look like this. It says the title here and here, and the canvases are there. If we open the console and actually go to these elements, we can see here the two canvases. They're just transparent and not marked in any way. I would also like the things to align, so this is like a title. And I will do that with a little bit of styling here in the head section. So let's define the style like so. The body will have text aligned to center. And the canvas, I'm going to give it a solid outline so that we see it. And let's give it also a little bit of margin so that the outlines don't touch. Let's save this, refresh, and now things look better. What I want to do is draw points on this left canvas at first. And we do that using JavaScript. So I'm going to go here at the end of the body section and start the script tag. I will call the 2 points A and B, and A is going to be initialized as 100, 150. And now we need to write some code to draw it on the left canvas. So let me get a reference to the context element from the left canvas, and I will use the 2D context this time. And let's begin a path. I will set the fill style to be black, and I will draw an arc at the A, X, and Y like this. This is where we will specify the size of this arc, of this circle there. What we need to say here is actually the radius. So if this size is going to be a global variable for our dots, this is where we specify half the size to be the radius. Let's define the size here at the top. Maybe 20 pixels is a good value. And now continuing here, this arc method also needs to know the starting angle, so 0, and the ending angle is 2 pi because we want the full 360 degrees or 2 pi radians to make a circle. We also need to fill this if we want to see anything on the canvas. So let's save this, refresh, and this is our dot now at 100x and 150y. Remember, the 0, 0 point is here in the top left corner. But I will soon draw another point, B, and I want to know that this is A, so let's write A on it next. After we draw this fill, I'm going to set the fill style to white because I want to draw on top of that black color, and I will fill text saying A at A.x and A.y, like so. Let's save this, and refresh, and it works, kind of. It says here A, but it's really, really small. Let's make it bigger. Let's make it relative to that size we defined previously. So I'm going to go here and say left context font size pixels, and let's make it Arial font. Refresh. It's bigger, but it's not aligned properly. We want it to be aligned to center and middle, respectively. So let's go here and say text baseline to middle and text align to center. Save, refresh, and now it looks the way I want it. It's time to add another point, B. So let's go to our code, and here at the top, let's say that B is going to be 200 and 250. And now to draw B, I could copy everything here, but that's very bad practice, so we should extract this as a function. Maybe draw dot on a given context. It's important to specify here because we will have another context for the right canvas. And then given a position and a label, because these are the two things that we have here. In this case, AX, AY are the position, and lowercase a here is the label. So this function will need to edit. So we have here the context for all of these instead of the left context, like so. And the position here, position X, position Y, position X, position Y, and the label goes here. And now we can call this function like so. On the left context A and the lowercase a, and we can call it again also on the left context B, the lowercase b. And when we refresh, we get both points now, but no duplicated code, so we're good. Now let's start using this right canvas next and just draw the same things over there as well. I'm going to get an access to the right context the same way as before from the right canvas here. And after we draw the dots on the left context, let's draw the dots also on the right context. Like so. If we refresh, we get this. It's the same thing, just on the other side. But now I want to change some things. I want to calculate the angle between A and B and then rotate the canvas on the right before drawing the points. You'll see. We get this angle here using the atan2 method. I do have a video on vectors where I explain this function really well. Check it out if curious. But here I just use it, so we need to pass here the difference on y and the difference on x, and that gives us the angle. And we use this angle to rotate the context by minus the angle, because I want to go counterclockwise, and then just draw the things there. And what we get is this. A and B are now horizontal like that. We also want to translate this canvas so that the top left corner is not 0, 0, but the coordinates of A. We do that by typing here translate by minus AX minus AY, like so. And now we get this. A is here in the top left corner and B is somewhere here. And now if we would have some kind of ruler there, B would say exactly the distance between A and B from the original canvas here. So what we will do is we will get the pixels in this top row from there and then find the maximum pixel that is colored by the dots. And that will be the far end location of this B dot. From that we subtract half the size, and that will be the distance without using the Pythagorean theorem. Let's first get the pixel values of that top row. After we do the drawing, we can get the pixel information, the image data, using the getImageData method. And let's write here the full canvas width, but only 1 as the height. So starting at the 0, 0 point, we go all the way towards the right, and just the first row is what we are interested in. Now, from here, let's log the image data so that we see how it looks like. And if we refresh and open the console, this is how an image data looks like. It has a width of 500, which is what we expect, and a height of 1, so we only get the top row of pixels. But this data array here has 2000 elements. This is 500 multiplied by 4, because each pixel has 4 components. A red, green, blue, and alpha is the opacity component. So we will be interested in just these alpha values. Every third element here is what we will want to look at, because all the others are color information that we don't need. The canvas is fully transparent, so the alpha is 0, except for where we draw these dots. I want to know where the dot exists. So we will filter out every fourth item from this data array here. So I don't really need the whole image data. I can just take the data from there, and I will use object destructuring like so. And here, let's take every fourth item as the alphas by filtering this data. And I won't care about the element there, but I will care about the index. I will only take those at every third index, or in other words, if the remainder when we divide by 4 is 3. So let's log these alphas here now. And these look different. It's 500 values, just as the number of pixels. And you can see here, it starts with some visible pixels, and that's this part of A here, followed by a lot of transparent pixels. So that's all these zeros here. And eventually we get the B section here. So these are the opaque pixels. And notice they are not all 255, which would be maximum opacity. Some of them are semi-transparent, and that's because of aliasing. When we draw something round like a circle, some pixels on the edge are semi-transparent here. It makes the object look more round. So anyway, keeping that in mind, what we need to do is find this index here, 151. This is the distance up to this point, and then subtract half the size, and that will be our center point of B. So the distance will be probably 140, 141, somewhere in the middle here. Let's do that. We don't need this logging anymore. Instead, I will initialize I as the last index in the alphas array. And then while it's greater than 0, if we are dealing with an opaque pixel, so non-zero alpha, then we break. We found the first visible pixel from the right, which is the one that we're interested in. So when doing this search, we also need to decrease I. And then our no Pythagorean theorem distance is going to be I minus half the size, like so. And let's log it into the console. Refresh, and it's apparently 141. Now, how good is this value? I don't know. Maybe we use the Pythagorean theorem to calculate the distance the usual way and compare. So let's go here and calculate Pythagorean distance. And this is going to be using the math hypot. I do have a video on the Pythagorean theorem, and I show multiple ways of calculating the distance. So check it out if interested. But here we just say the difference on x and the difference on y. And that's the Euclidean distance between a and b. We log it here as well. And to make things more clear, let's write here no Pythagoras. And here Pythagoras. Refresh the page, and we get 141 without Pythagoras, and with Pythagoras we get 141 point something. So it's a close enough approximation, and in practice this kind of pixel level precision is all you need really for many things like games and stuff. So it's good, but we can even do a little bit better if we take into consideration those semi-transparent pixels there as well. Like here we could say plus alphas of I divided by 255. We need to normalize because 255 is a large value. We want it to be 1 at maximum when it's fully opaque. So let's save this, refresh, and it's getting even closer to the real thing. But again, this level precision is often not needed even. And come to think of it, this value here is not correct either, because I specifically chose these points so that the true distance between them is 100 times the square root of 2. And that has infinitely many digits, but this doesn't have infinitely many digits. So the result is actually wrong. But on computers, we often just deal with approximations, and they are good enough. So this works now for this particular A and B, but how about other ones? I'm going to implement a way to move A by clicking on the canvas, and we will move also B by right-clicking on the canvas. So let's go here at the top, below this size, and add an event listener to our left canvas for click. And given the event information, I'm going to first get the position, get the mouse position from this event information, and then set a x and a y to that position, and then redraw everything. So now what we need to do is implement this get mouse pose function, and then redraw will just be everything that happens here as a function. So I'm going to write here function get mouse pose from the event, and what we first need to do is get the bounding rectangle of the canvas. The canvas is this event.target, and get bounding client rect, and here we return the xy coordinate where we clicked by saying the client x and subtracting where this rectangle starts at. So the left side of the rectangle, and the same thing with client y and rectangle top. This is our get mouse pose function, and the redraw function here is just everything underneath. So everything here goes inside that, including this console logs. We want to get updates on these distances every time we click. And because we are going to draw on the canvas multiple times, we have to clear it here at the top before redrawing again. So I'm going to do that for both canvases. I will take the left context and clear rect the whole canvas width, canvas height, and I will copy this for the right context, canvas, I mean. Okay, and now if we save and refresh, the points are gone. And they are gone because that redraw function is not called until we click on this canvas somewhere. And if I'm going to click maybe here, you can see A is now here at my click location, and this is where B is. This distance looks proper here. And if I'm going to click somewhere else, like maybe here, something strange is happening here on the right. So the thing is, when we rotate and translate that canvas on the right, we're going to rotate and translate again and rotate and translate again, and a mess will happen. So we have to reset the canvas before we did this translation and rotation every time we redraw. So two things to fix. First, I want to see something when beginning, and that's really easy. I just call this redraw function somewhere here at the top. And the other thing is not too difficult either. What we need to do is here, save the state of the canvas, and at the end of everything, restore the state so that the rotation and translation goes away. Now I'm going to save this, refresh, and now we see the original A, B locations without clicking. And if I click on A here, this B has moved. And if I click here, B moves again. And everything here looks proper no matter where I click. And these distance values also look pretty good, no matter where A is. Let's do the same for B real quick. So I'm going to go here at the top and copy this code. But instead of click here, I will write context menu, because when we trigger the right click context menu, that's when I want this to move B here. I also don't want that menu to appear. It's really annoying. So I will write here prevent default. And now if I refresh and we click here with the left click, it moves A. And when we right click, it moves B, and everything seems to look just fine, no matter where A and B are. So we do have now two ways of calculating the distance, one with the Pythagorean theorem and one without the Pythagorean theorem. So which is better? Well, I already said that the accuracy here is pretty good for most applications. So what's left to compare is the speed. Let's measure how fast they are. I'm going to go in this redraw method, and after we save here, when we start to calculate the angle, I will write start time is performance now. And then after we have calculated everything, but before we print this no Pythagoras distance there, I don't want to measure the printing as well in the console. So here we say end time is performance now. And here I'm going to go at the end, and I will also concatenate with, on a new line, end time minus start time plus milliseconds. So this is going to be how many milliseconds it took to calculate the distance without the Pythagorean theorem. And refresh. And we have here 3.8 milliseconds, which is really fast. I mean, really, really fast. 3 milliseconds is nothing. And actually, if you click here a few times, you will see that this number of milliseconds is changing. And after you click a few more times, it will drop significantly. So I think that this canvas has some kind of way of optimizing some of these operations. We even get below 1 millisecond with some of these calculations now. But let's do the same for the distance calculation here using math.hypot and see what we get. So I will say here, start time, let's reset it to performance now, and end time, performance now. And here I'm going to print the same thing pretty much as before, like so. And let's add a new line here, console log, and I will make several dashes like that so that we separate the two logs in the console. Let's save this, refresh, and this second one doesn't even register here. Normally, when you do these kind of measurements, you would repeat the operation many times and take the average value or something like that. But in this case, it seems like the other one really doesn't even register anything. And the distance using the complex way of rotating, translating, does register something. So I think we can safely say that the Pythagorean theorem is faster. What do you guys think? Let me know in the comments and see you guys.